వెంకట్ సరే ఏమొస్తలేదు సార్.
మ్యూట్ చేస్తున్నాను చూడండి. షేర్ స్క్రీన్
క్లియర్ కదా సారీ.
Okay, sorry students, there was some technical issue. Okay, now see in the previous problem that what we discussed, just see the numericals and try to understand physically what it is going to represent. The probability of occupying an electron, if you see, okay, at a particular energy state in the conduction band, EC plus KT by 2 corresponds to which band? Obviously it is in the conduction band. Okay, how much you got? It is 3.9 into 10 power, I think it is -5. I'm sorry, it is -5, not +5. Please correct it. It cannot be +5. Okay, that much probability, because probability is less than 1. No, please correct that. It is 10 power -5. Okay, so it is a very small value. Yes or no? It's a very small value, but still concentration of the electrons, you can see it is order of 10 power 15 per centimeter cube. So what you can understand here is, because there are large number of available states that are present in the conduction band, even though the probability is very less, you can find, okay, large number of electrons in the conduction band, because if you consider how many number of available states are present in the conduction band, compared to that, this value is going to be less. What is that value? 10 power 15 value is going to be less. In that way you must understand. Okay, hope I am clear. Yes, yeah. Now let us go to the next one. Okay, so it is related to the, we need to find out concentration of holes in the valence band. Okay, so we know what is the formula for concentration of holes. Okay, again it is the equilibrium. So let me write the formula first, and then we'll see what are the parameters that we are going to require. So P naught is equal to what? It is NV e power minus EF minus EV. Okay, but the temperature where you have to find out is the 400 Kelvin. Please keep it in mind. Okay, but parameters that are mentioned here is related to 300 Kelvin. These are related to what? 300 Kelvin. Now I want to use NV as well as KT. So first we need to find out NV as well as KT at 400 Kelvin first. Am I correct? Okay, because you need to find out at 400 Kelvin. Okay, so the key point here is what? We need to obtain NV and KT at 400K, and we know anyhow at 300K what will be the value. From that we can calculate it. Okay, now we know what is NV. What is NV? 2 times of 2 pi mn KT divided by h square whole power 3 by 2. So we can very clearly see NV will be proportional to T power 3 by 2. Am I correct? NV is proportional to T power 3 by 2. So if that is the case, can I say NB, okay, at 400K is equal to NV at 300K, okay, into what? 400 by 300 whole power 3 by 2. 400 by 300 whole power 3 by 2. Yeah, I am using very simple mathematics. You know, NV at one temperature, I am calculating in the other temperature. Is it fine? Okay. Now this is equal to NV at 300 is how much? It is 1.04 into 10 power 19 into 400 by 300 whole power 3 by 2. Okay, so you calculate this value. This will give 1.6 into 10 power 19. What are the units? Per centimeter cube. Okay, per centimeter cube. Hope I am clear. Now how to obtain KT? KT also you have to find out, because KT at 400 Kelvin, can I say KT at 300 Kelvin into what? 400 by 300. Yes. So what is KT at 300 Kelvin? It is given 0.0259 into 4 by 3. So you calculate this value. So this will be 0.03453 electron volts. Okay. Am I clear? Okay. Now we know NV at 400 Kelvin, KT at 400 Kelvin. We just put it into this equation. What is P naught now? P naught equal to, it is NV is how much? 1.6 into 10 power 19. Okay. Into E power minus of what is EF? Yes. The problem it was mentioned. Assume that the Fermi level is 0.27 electron volts above the valence band. So what is this value actually? It is, I can say, can I say EF minus EV? Yes sir, 0.27 is nothing but EF minus EV. Am I correct? Okay, so it is minus 0.27 divided by 0.03453 electron volts. Okay, so we calculate this, we will get 6.43 into 10 power 15 per centimeter cube. Okay. Yes. So here what you have to understand is, if I know the parameter values at a particular temperature, you can calculate the parameters in at some other temperatures also. That is what we have done here. Okay. Now this NV and NC, if they have not mentioned, they are not varying with respect to temperature. Okay. Then you can take them as constants. Okay. But here he has very clearly mentioned at a particular temperature NV KT, and he is asking at some other temperature. So we need to substitute what? We need to calculate for 400 Kelvin also. Okay. Otherwise you can take them as constants. Okay. Hope I am clear. Yes. Okay. So this is how we can calculate. Okay. So let us go to the next. So what you need to find out here is calculate the intrinsic carrier concentration, okay, in silicon at 250 Kelvin and 400 Kelvin. Okay, not at 300, okay, but 300 they are going to give the value. Now, the values of NC and NV for silicon is given at 300 Kelvin, okay. Assume the band gap energy of silicon is given, and it is not varying with respect to the temperature. It has very clearly mentioned here, okay. So because energy gap also changes with temperature, no, so it will be complicated. So that's why it has given it is a constant, okay, and KT value is also given, okay. Now let me write, okay. So where we need to find out now, 250 Kelvin, 400 Kelvin. The given values are at room temperature. Is it fine? Okay. Yes. Now we know very clearly what is the formula for Ni. Let me write that, and then we'll go for the solving this. Okay. So what is Ni or Ni square? I'll write Ni square is equal to Nc Nv. Okay. Into e power minus Eg divided by Kt. Yes, sir. No, this is the formula. Because Nc Nv are given, I am writing in terms of Nc Nv. Okay. Hope I am clear. Now let us consider T is equal to 250 Kelvin. Okay. So please try to concentrate the equation that I am going to write now. Okay. So Ni square is equal to, okay. So at 300 Kelvin, we know what are the values of Nc Nv. Let me write that first. 2.8 into 10 power 19 into Nv is how much? 1.04 into 10 power 19. Yes sir. Yes. What is the term that I need to write here? If you remember the previous problem, Nv is proportional to T power 3 by 2, and Nc is also proportional to 3 by 2. Yes. So Nc Nv proportional to what? Tq. So can I write now, because I am calculating at what temperature? 250 by 300 whole power 3. Hope I am clear with what I have written now. Yes. Okay. Into e power minus Eg is given how much? 1.12 electron volts divided by, what about kT? Can I say 0.0259, okay, into 250 divided by 300, because I need to find out. Okay. Now if you have any confusion, separately calculate NC, separately calculate NV, calculate kT at 250 Kelvin and try to follow this. Okay. I am putting in one equation. Okay. Hope I am clear. We find out this. Okay. You find out, you will get Ni value is equal to 7 into 10 power 7, okay, per centimeter. Okay, per 250 Kelvin I am calculating. Okay. Now in the similar way, try to calculate at 400 Kelvin now. Let us consider T is equal to 400 Kelvin. Okay. Now Ni square is equal to again NC NV, okay, T cube, okay, proportional to T cube. So it is 2.8 into what, 10 power 19 into 1.04 into 10 power 19, okay, into what, 400 by 300 whole cube, okay, into e power minus Eg is the same 1.12 divided by kT 0.0259, and we need to find out at 400, multiply 400 by 300. Okay, hope I am clear. So you calculate, this will give 5.67 into 10 power 24 per centimeter. Ni square is this, and get what is Ni from this. Is 2.38 into 10 power 12 per centimeter. Okay, am I clear? So this is the answer for Ni at 250K. This is for 400K. Okay, hope I am clear. Now, see how you can mathematically, if you see, we can clearly observe that as you increase the temperature, what is happening to the carrier concentration? It is increasing. You can very clearly see. Okay, from 250K, how many you are having? This one, 250K, 7 into 10 power 7 per centimeter cube. When you go for 400K, it became order of 10 power 12, 10 power 7 to 10 power 12. That almost 5 orders of magnitude has been changed with 150 Kelvin variation of the temperature. Okay, so how you can understand this? Because as you increase the temperature, more and more number of electrons can move from valence band to conduction band, creating the free electrons in the conduction band. There is a vacancy, nothing but a hole in the valence band. Okay, hope I am clear. Yes, please, whatever the numericals we are working, try to understand physically also. Okay, so that you can have better understanding of the concept. Yes, okay. 1 second. Yeah, let us move to the next question. Calculate the position of the intrinsic Fermi level with respect to the center of the band gap in silicon at room temperature. The density of states, effective masses. You can clearly see he has mentioned density of states, effective mass. Okay, so Mn is given, Mp is given, both are okay. Now let us write the equation that we have derived for the Fermi level. What it is? Ef is equal to Ec plus Ev divided by 2 minus Kt by 2 Nc by Nv. Am I correct? I'm sorry. Kt ln. Ln is there. Logarithmic function is there. No, I'm sorry. Kt by 2 ln of Nc by Nv. And we can write what is Nc Nv, and to cancel the terms, the same equation I can write it as what? Ef equal to Ec plus Ev by 2 minus Kt by 2 ln of Mn by Mp whole power 3 by 2. Yes. Now if Mn is approximately equal to Mp, we got it as Ef is approximately equal to Ec plus Ev divided by 2, because this ratio will become 1. Logarithmic function of 1 becomes 0. That's what we have represented. Okay. Yes or no? Okay. So let us take, this is EFI. Please try to understand. Okay. Again, notations, it's your convenient way. Okay. So you can write EI also. There is no issue with that. Okay. Is it fine? Okay. But for our condition, Mn is not equal to Mp. Okay. In the given problem, Mn is not equal to Mp. Okay, so you just substitute whatever the values, and you can get it. So Ef equal to Ec plus Ev by 2 minus Kt by 2 ln of. So Mn is given how much? It is 1.08 m naught. Okay, I'm not writing m naught. It will be cancelled. Mp is 0.56 whole power 3 by 2. Okay, got it? So you calculate these values. Okay, we know. So it is Ec plus Ev by 2. Okay, you can take 3 by 2 to this side. Then what it will be? 3 Kt by 4 ln of 1.08 by 0.56. Okay, it's only the simplification. Okay, you can do that. Okay, Kt value is also given. So you calculate this value. I can write this one as Ef equal to Ec plus Ev by 2 minus 0.0128 electron volts. 0.0128 electron volts. Okay, so what is the meaning of this? Where it is going to be located now? We can see we have taken Ec plus Ev by 2 as EFI. Nothing but what? Intrinsic level when you take Mn equal to Mp. Nothing but the middle of the energy gap I can call. So can I write now EF is equal to, this is EFI minus 0.0128 electron volts. Okay, so can I write now this one as EF minus EFI is equal to minus 0.0128 electron volts. So how you can interpret? Yeah, in the options you may get, actual Fermi energy level is above the middle of the energy gap, below the middle of the energy gap by this value. That you must identify now. Okay, so how you can identify? What is EFI here? It is the middle of the energy gap. Okay, so if this is the middle of the energy, I am getting the negative value. What is the meaning of it? Okay, yes, what is the meaning of this? Yes, EFI, that is what middle of the energy gap we have taken. So EF is less than EFI, no? Because I am getting the negative value. EF is less than EFI means it is located below middle of the energy gap by 0.0128 electron volts. Okay, so let me write that point. EF lies below the middle of the energy gap, by how much? 0.0128 electron volts. Okay, yes. Can I conclude this? Yes. Okay. Now, again, try to interpret whatever the theoretical part that we have discussed to this numerical value. Now, what is Eg by 2 for silicon? No, for silicon, Eg by 2 is how much? 0.55 electron volts. Okay, let me write here. Okay, if I consider silicon, what is Eg by 2? It is 0.55 electron volts. Now compared to this, you see what is the value of, you got it, 0.0128 electron volts. You compare these two, almost I can neglect this. That is the reason why we are taking Fermi energy level is located approximately at the middle of the energy gap. Okay, hope I am clear. Yes. So the reason is, you can see there is a logarithmic function. No, so this this logarithmic function will make what, even though this variation is large, when you take it logarithmic, its value is going to be less. Okay, so you can compare with the values, numerical values, and you can interpret that to the discussion that we made theoretically. So in theoretical discussion we made what, it is approximately at the middle of the energy gap, and you can see we got the almost the similar type of thing here. Okay, so hope I am clear with whatever the problem that we have discussed. Okay. Clear? Yeah. So now we'll go for doubts, because I need to start the new topic. I think almost your intrinsic semiconductor material is completed. Okay, intrinsic. Now again I'm repeating, go and get thorough with whatever we have discussed yesterday and today with respect to the intrinsic semiconductor material, that is bond model and band model. And the same thing is going to be repeated for the extrinsic, but with a little bit modifications. Okay, we'll see what those modifications and how we can do that. Okay. Yeah. Now
Hello.
yes, please.
Good afternoon, sir.
Very good afternoon, please.
Sir, page number 68, sir.
Yeah.
Sir, 56, sir.
56,
Sorry,
sir.
56.
Fine. Yes, please ask the doubt.
Sir, here Fermi level down 0.3 eV is there, sir.
Fermi level.
Fermi level down 0.3 eV. If we take Fermi level down 0.4 eV means the electrons will be present, sir.
No, I'm not getting your question.
Here the probability that a state 0.3 eV below the Fermi level, sir. If probability is 0.4 eV below the Fermi level, then there will be electrons present.
Yeah, you
How much-
calculate. You calculate.
Okay, sir.
Instead of 0.3, you put 0.4.
Okay, sir.
Fine.
If the electrons in surface of EV will be transfer more efficient than the bottom, sir.
No, come again.
The electrons in the surface of EV.
Surface means you are talking about very close to EV.
Yes, sir.
They
They will transfer very fast
obviously.
than the down particle. Down
Obviously. See, suppose if you have 5 meter, 2 meter jump, which one is easy for you?
2 meters.
Obviously, that's the same thing here also, no?
Okay, sir.
If energy difference is increasing, I'm sorry, we need to put more effort. So obviously, it's going to be easy when you are taking the close to the EV.
Okay, sir. Thank
Right?
you. Sir.
Yeah.
Thank you very much.
Yeah. Harsha, please.
Hello?
Yes.
Sir, am I audible?
Yes. Please go ahead.
Sir, in intrinsic semiconductor, there is no concept minority and majority, no, sir.
Obviously.
And in Fermi Suppose if we are increasing the temperature,
Hmm.
the F is getting down, no sir, near
Yes.
to the valence band.
Yes.
So then the conduction will be due to the holes.
Conduction
Is
band.
it right, sir?
Conduction band. Come
Valence
again.
band, sir.
No, come again. Come
If
again.
we are
If you are increasing
if
the
you are increasing the
temperature,
temperature,
uh, uh,
the Fermi level will
hmm,
come downwards, no sir, near to the
obviously.
valence band.
Yes. Yes.
So
Uh,
the conduction will be due to the holes, no sir.
Conduction due to why it is holes. How you are getting holes? What is the hole? What
So
is
it
a
is due.
hole? What is a hole?
It is a vacant space created by when the electron
Uh,
is not occupied.
when electron complete it.
If
When electron
when electron creates a vacant space
creating
by
means
leaving
how where that electron gone.
to the conduction band.
Obviously, so because both you are creating, no, you cannot see in the semiconductors. With the very beautiful thing with the semiconductors is if you create an electron, correspondingly there is a hole that is going to be created.
Yes, sir.
Okay, are you understanding?
Yes, sir.
So
Yes, sir.
even though you are getting the excess carriers, but still it is going to be electrically neutral. That is the beautiful nature of the semiconductor material.
Yes.
Are
Sir,
you
what
getting
actually is Fermi level? I'm getting confused, sir.
what
What
actually?
actually defines the Fermi level?
We have seen physical significance of Fermi level or not?
Yes, sir.
What are the statements that we have given there? What is the statements that we have given in the physical significance of Fermi level? At absolute zero, all the energy levels which are present below the Fermi energy level are filled, and all the energy levels which are present above the Fermi energy level are empty. That is the
Yes, sir.
significance. And if
Yes,
you
sir.
take at temperature more than 0 Kelvin, exactly half of the available states are going to be occupied. Suppose in the valence band there are 5 into 10 power 10. For example, I am taking 5 into 10 power 10 available states, and let us take in the conduction band also same. I am having 5 into 10 power 10. At any point of time, how many number of states are going to be occupied? Exactly half.
Okay.
When you make the electron to move from valence band to conduction band, okay, you are not making your electron to move out of the crystal, but still it is present. So as a whole, you consider valence band and conduction band, how many are going to be filled? Always it is the same.
Yes, sir.
Are you understanding? Only
Yes,
the
sir.
thing is to modify the electrical properties, you want to make your electron to move into conduction band, because the electrons which are present in are responsible for current.
Yes,
Are you
sir.
getting? Are you getting?
So, yes, sir. So it just defines the
Hmm.
number of states, like how it
No,
is acting.
not number of states. Not number of states. See, it is one particular energy level with which we can do many things. Later on, you can see where if you want to draw the energy band diagram, we are going to start with the Fermi energy level. You are see,
So
it's
according,
yes,
so according to the position of the Fermi level, we get to know that from like
yeah.
where the number
See,
of.
we'll go when you are discussing about the extrinsic, you will get more clarity, because here in intrinsic semiconductor material, we have concluded is at middle of the energy gap. But
Yes,
you go for N type and P type, the location will be different, and we'll see what the
yes,
significance there. We'll discuss in detail. Don't worry. Okay, we'll get clarity.
yes, sir. But in problems here, we are getting the
Hmm.
Fermi level like in the before the last problem.
Mm-hmm. Last but
There
one
we
problem.
got,
Huh?
yes, sir.
Hmm.
There the Fermi level we have considered like in the question they
Okay.
have given the
Which
Fermi level
this question?
not exactly in the middle.
Yeah.
Last
No,
second, sir.
last question. Last question. Yeah, because your Mn is not equal to MP, man. That is what we. If you understand, that is the reason why I have given. Finally, I have compared with the numerical. No, the energy. Suppose if I consider the silicon, Eg by 2 is how much? 0.55.
Yes.
Now you got how much here? How much difference is there between the middle
0.55.
of the energy gap and EF? It is 0.0128. No, can I neglect this 0.0128 with respect to
0.08.
0.55?
Yes, sir.
That is the reason why you are taking most of the times it is at the middle of the energy gap. It is taken for granted for intrinsic semiconductor. Fine. Yes. Hello.
Okay. Yes.
Okay. Yeah. Fine.
Yes, sir.
Hmm.
No, yes, I got it, sir.
Okay. Yeah, Nazir. Nazir Jamal, please. Nazir Jamal. Yes. Nazir Jamal. Abhinash.
Good afternoon, sir.
Yeah. Who is talking? Abhinash.
Yes, sir.
Yeah,
Good
please go.
afternoon.
Very good afternoon. Please.
Sir, can you explain me that effective band diagram?
Effective.
Effective band picture, that how you draw that rectangular at EC and EV. Effective band picture.
This one.
Yes, sir.
We have drawn in the correspond when you are discussing about concentration of electrons, concentration of holes. We have drawn, no?
Yes, sir. At that time the connection was weak, sir, so I couldn't hear that.
Okay. See this whatever equation that we got for electrons, n is equal to what we got. It is nc e power minus ec minus ef by kt. No.
Yes, sir.
What is nc there? We have represented. It is the effective density of states at the edge of the conduction band. Now, our interest is going to be only near the edges of the band, either it is conduction band or valence band. Okay.
Okay.
So instead of representing complete n of e here, what we are going to do is we are considering only the edge, no. So
Yes.
we are replacing that entire n of e with effective density. Okay.
Okay.
So it is in a delta function. What is the area under this? Is give nc. And similarly, at the edge of the valence band also, we have done the same thing. Instead of representing complete n of e, I am just putting nv.
Okay.
Got it?
So,
Got it?
yes, sir. One last doubt, sir. Sir, how
Yeah.
that EC plus EF by 2 is equal to EG by 2?
Think, man. Think. It's a simple thing. Try to get it. Okay. Okay. Any other doubt?
No, sir. Thank you.
Yeah. Okay. Nazir Jamal. Tejashree.
Good afternoon, sir.
Very good afternoon, please.
Sir, in page 54,
54. Yeah.
sir, 54, sir. Yeah. Sir, you said about quasi-continuousness, sir. Why did you mention about that here, sir? I didn't get it. And what?
Continuous means what?
Uh,
Continuous means there is no. See, with respect to energy, if I talk, continuous means, okay.
Yes.
So you don't find any discontinuity, no?
Yes.
Means there is no gap. Suppose one energy level and another energy level.
Yes.
Okay. But here you can see what is the change in energy we got 5.7 into 10 power minus 9, no?
Okay.
And actually electron volt is what? 10 power minus 19 orders.
Yes.
Okay. So what is the order of difference here?
10 orders.
Okay, even though maybe for us it is small, but you compare one energy level with another energy level, this is a larger value. Am I correct?
Yes.
Okay, so it's not continuous, but there will be some E1 to E2, there will be some difference.
Okay.
For us it is small, but for them it is not. So that's why I mentioned quasi-continuous.
Yes, sir. And sir, another doubt in page
Yeah.
63.
63.
Yes.
Please.
So actually, we consider the energy gap between EC and EV as EG, no, sir. In 63.
63 only, no?
In next page, sir.
This one?
The place where we have concluded that when mass of electron, effective mass is, Mn is equal to MP.
You are talking about
we
Fermi
have-
energy level, huh?
Yes, sir. EF, Fermi energy is half of the EG by 2.
This one, huh?
Yes.
66, yeah.
Yes. So in general, we consider EG as EC minus EV, no, sir. Then
No,
how
I'm
did
not
we?
getting. Come again. What is the statement that you have given? Generally,
So generally, EG energy gap is the
Hmm.
energy between conduction band and valency band, no, sir.
obviously.
So then, how did we consider here EC plus EV as EG, sir?
EC plus EV by. See, you just think, okay, whatever I have given, you just think, okay. Otherwise, I'll clarify tomorrow. Say, I think some other person also asked the same doubt. Try to
Yes.
spend some time. You draw the energy band diagram and try to think how we can get it easy by.
Okay.
Fine, okay.
Yes.
Ah,
Thank you.
okay. Yeah, Krishna.
Hello, sir.
Yeah, please.
Sir, in page 54F,
50. Please go ahead. Go ahead.
sir, there the topic of quasi-continuous energy level has come by comparing delta E with 1 EV value, na, sir.
Hmm.
But delta E is kinetic energy. 1 EV is just a value, na, sir. How can you compare kinetic energy with that value, sir? We
Yeah,
need to compare without, we need to compare it with E1 and delta E, na, sir. If we want to find any change.
Come again.
That I didn't understand, sir.
We need to compare with
This is
what?
kinetic energy and that is 1 EV value.
How you are representing your kinetic
Sir,
energy?
delta E is kinetic energy.
Please, 1 second. How you are representing kinetic energy in terms of what you are going to represent? In terms of
Electron.
that's what I have done, no?
Yes, sir. But this you are comparing it with 1 EV value, no, sir. That I didn't understand. Why are you comparing?
See, the measure that you are taking for electron energy is what?
Electron volts.
And here, man.
Sir, I didn't hear your voice, sir. Hello.
We are representing the energy of the electron in terms of electron volts. Am I correct?
Yes, sir.
What is this change in kinetic energy? How you can physically represent, or what it is? If you are giving higher energy, electron is moving to the higher energy level. That is what the kinetic energy is.
Are
you getting?
Yes, sir. Yes, sir.
That's what I have compared. Why I am not supposed to compare 1 electron volt with delta E?
Okay. But why there is a need to compare, sir?
To give some important conclusions, man. Mathematically, whatever we have represented, from that we should understand the physical concepts, no? It's not only mathematics. You need to understand the physical concepts also.
Okay.
For that I have compared.
So how is that quasi-continuous related to it, sir?
Have you not listened?
I didn't get that point from that time, sir. I didn't understand, sir.
Continuous means what?
There is no break.
But here you can very clearly see one energy level and the other energy level are going to be separated by a small value actually. That is the reason why I am calling it as quasi-continuous.
Oh, that small value is given as delta E.
Yes.
Okay. Now I got it, sir. Sir, and another doubt is, why are we considering only the concentration at the edges of CB, sir? I mean, edges of conduction band or valence band.
Where suppose you move the electrons from valence band to conduction band, where from you can able to move first?
From starting. I mean, from top of valence band to bottom of conduction band.
That is nothing but what? Edges, no?
Achha, so we'll consider only about the first one.
Yeah, that will be enough for us. Because
sir,
when you are going for deep into the bands, things will change, and that is not required for us.
Okay, sir. Sir, and one more, sir. Sir, Boltzmann approximation, it means that if E minus EF, if energy level is greater than 3 kT, then the probability of occupancy is less. Is it right, sir?
No. It's not. See, not only that, once your energy level is more above EF, the probability of occupancy is less. Not only E minus EF greater than 3 kT.
Then
once
why
you are...
only... yes, sir.
Please come again. Why only?
then why only we are considering it as only 3 kT, sir?
Yeah, that, see, any approximation, what you will do, certain conditions they will do, no, they will give certain, you know, experiments and all they will do, and they will give certain, finally some conclusion.
Okay.
Okay,
If
so
it is minus, yes, sir. If it is
so
minus 3 kT, sorry, sir.
if it has
If
3
it is
kT,
minus
that will be 3 kT will be sufficient in all practical purposes. They have done some experiments and finally they have given that 3 kT.
Okay, okay. Sir,
Okay,
and minus 3 kT means the probability of occupancy of holes is very less. Unoccupancy of holes.
No, here don't get confused.
Hello?
You see,
Hello?
yeah. Are you
Hello,
able to
sir?
hear me? Are you able to hear me? Hello.
Yes, sir. Now I'm able to hear you, sir.
Yeah.
Yes, sir. Now
See,
yes.
don't get confused. Okay. See, if you
Yes,
know
sir.
what is the, you know, probability of occupancy of an electron, obviously you know what is the occupancy or unoccupancy in the valence band. Because f of e comma t, you know what is 1 minus f of e comma t is obvious.
Unoccupancy. Okay, okay. Sir, and last doubt, sir. In finding the concentration, right from today's starting class, while finding the intrinsic concentration, why are we considering that Fermi-Dirac graph also, sir? As it will be physically present in the semiconductor, is that the reason?
No. See, whatever the bands that we have represented here, are you thinking that physically they are going to be present? So it's only our way of representation, convenient way of representation to understand the concept. Okay. Now coming to your question, one second. Coming to your question, why we are representing f of e comma t, I have very clearly mentioned in the energy band diagram band model, there are three principles, no? What they are? Allowed states, then how they are distributed, and what is the fraction of occupied states. So if I put these three things at one point, I can able to get the information about how many number of electrons are going to be present in the conduction band, how many number of holes are going to be present in the valence band. That is what I have done in the graph that I have represented.
Oh, so for the principal 3 also we are including it using that Fermi-Dirac graph.
Yes,
By
that's
finding the concentration.
Yes, that is what I have mentioned very clearly.
Okay, so effectively only this will be present, right, sir?
Yeah.
Sir, and last doubt, sir. Sir, in that is in effective band picture, we are drawing that band of energy level at NV, no, sir? NV or NC.
Yes.
That rectangular box.
Yes. It is a delta function. It's not rectangular box.
Sorry, sir. Delta function. But even though it is present over such a wide length, the effective will be present only within the small area, right, sir? That is the area under which the
it is near, very close to your conduction band and very close to valence band.
But within that entire band, our electrons or holes will not be present, right, sir?
It will be present, man.
Sir, but according to that graph of Fermi-Dirac
function. One second. Yeah, I got your doubt. One second. See what NC is going to represent?
Density.
How many number of I am talking, but I am not talking about where they are located. That is a different issue again.
Okay.
Are you getting? How many number of states are present? They will distribute. Obviously, they will distribute in the energy.
Within that energy band, equally they will distribute.
Yes.
But effectively, only small part will be present.
Not small part. That is our representation to understand concepts. We are representing like that. From that, where we have started, actually, if you consider, you know, a distribution of states in the conduction band, n of e we have represented, and in the valence band also n of e we have represented, but it is not required for us to represent entire conduction band and entire valence band. That's why I am taking only at the edges. And what I am interested is going to be again how many number of states are present. Those many states I am representing with NC and NV.
And within that, wherever the Fermi-Dirac graph crosses, that is the effective number of electrons, that is concentration in conduction band, right, sir?
No. Again, why what you are giving the last statement, there is a lot of confusion. There is no clarity about what you are asking.
Yes, sir. Sir, NC we have drawn that density, number of atoms in conduction band. but when we are coming to the concentration of electrons or
Hmm.
intrinsic concentration, we
Hmm.
are considering only that part of NC which is coming under that Fermi-Dirac graph, no sir.
See, that's what, one second. See, if you see the equation that we have given for n, how you calculate it, you are integrating, no? From, suppose you take the concentration of electrons, n equal to integral EC to ET, n of E dE into f of E comma t. Am I correct?
Hmm.
What that physically
Yes,
is
sir.
going to represent, you are calculating area under 3 different parameters. Wherever common thing is going to be that, that is going to be the n value. That is what we have calculated already. What is the doubt there? I am not able to understand.
Now I got it, sir. I thought that throughout that NC we will consider electron range. I mean concentration of intrinsic.
So okay, you got doubt clarified?
Yes, sir.
Okay, okay.
Thank you, sir.
Yeah. Yeah. SS,
Good
good afternoon, please.
Good afternoon, sir.
Yeah, yeah.
Sir, at room temperature, electrons from silicon band, matlab valency band to conduction band, they will transition take place, sir.
Fine. Takes place.
Energy gap is 1.1 electron volt, sir, but we are getting ET is 0.06 volt. So how the transition takes?
Come again.
Sir, at room temperature, electron from valency band they go to conduction band, sir.
Yes.
Sir, but energy gap is 1.1 electron volt, no, sir,
Yes.
for silicon temperature.
Hmm.
Room temperature we are getting ET as 0.02 to 26 millivolt, no, sir.
That is for what? KT equal to 26 milli electron volts for what? How many particles?
No, sir, it was okay. So 42 electrons. So,
Yes,
okay, sir.
yes.
That's
Now you got it. So it is not one.
Yes,
Okay, there are many things are involved to make your electron to move from valence band to conduction band. That you are forgetting.
okay, sir. So collisions takes place in the valency
Yes,
band
yes,
when
yes,
the
yes.
40 collide.
Yes, yes.
Thank you,
Yeah.
sir. But at t equal to sir, we got Fermi Dirac function is 1/2, na, sir. When E equal to EF, we get F equal
F
to
of E
1/2.
comma
Sir.
T equal to 1/2.
Forbidden gap, sir. There was no density. There was no energy levels, no, sir. Electrons to occupy. Either it go to conduction band or it has to stay in valency band only, sir.
Yes.
But we are getting by 2, no, sir. So it is tells the probability that occupying electron, no, sir. But how does it can occupy the forbidden gap, sir?
No, it is not the forbidden gap. That's what, if you see the statement that we have given, second statement, for T greater than 0 Kelvin, exactly half of the available states are going to be occupied. Available states are going to be present where? In the valence band and the conduction band.
Yes, sir. But Fermi Dirac is at equal to EF is 1/2, no, sir. It exactly.
You're not in a. Please listen carefully. What is the conclusion that we made if E equal to EF? Try to understand. Physically, it represents. I'm repeating the statement that I've given. Please listen carefully. It is the energy level, okay, where exactly half of the available energy levels are occupied once T is greater than 0 Kelvin.
Okay, sir. Okay.
I am not saying that wherever forbidden band is there, there are no energy levels, but you have the energy levels in valence band and conduction band, no?
Separated by that gap.
Yes. So available states will be in the valence band and conduction band only. Now suppose, I think same numerical example I've given, listen carefully. Suppose 5 into 10 power 10 states are present. For example, I'm taking to make you to understand. It's not the practical value. 5 into 10 power 10 states are present in the valence band. Let us take same 5 into 10 power 10 states are present in the conduction band also. Now you increase the temperature. What will happen?
Transition takes place.
From valence band to conduction band, electrons will move. But you identify how many number of empty states and how many number of filled states are there as a whole. Consider both valence and conduction band. It remains the same, no?
So same amount of electrons go, no? Same amount of holes created in the valence band.
Obviously. So that probability is half, means exactly half of the available states will be filled. It is both talking with respect to valence band as well as conduction band. I'm not talking about only one band here.
Okay, sir. Thank you.
Yes. Yeah, Rahul. Rahul.
Hello, sir.
Yes.
Yeah, so like the classification of masses, like on the conductivity and the other density thing. So, is there any other classification of mass?
Mass. Okay, you are talking about effective mass.
Yeah, effective masses.
Yeah, you can have different parameters. If you consider, you can have it.
Okay, like for example, what like other than these two,
Yeah,
are there any other?
as it is not required. Okay, you if you want, you can explore.
Okay, fine.
Is it fine?
Okay, sir.
Yeah.
Good
Yeah.
afternoon. Can you
Very.
hear?
Yeah. Very good afternoon, please.
So page number 64F.
Page number 64F.
Yes.
Please.
Sir, isn't this supposed to be ln instead of log?
Okay, that's I think I already mentioned. No issue. You can understand because there is an exponential term, it should be ln.
Oh, okay,
Yeah.
sir. Thank you.
Okay. Yeah, Rajavelu.
Good afternoon, sir.
Very good afternoon.
So my doubt is in 65 and 66 page one.
Yeah, 65. Come to 60.
You have mentioned like EC minus EV as energy band gap EG.
Hmm.
In 66, you have mentioned that EC plus EV is equal to EG.
Hmm.
So
Yeah, spend some time. I think same doubt has been asked for one or two people. I have already replied for that. I think you are not there. Are you there when? Are you there when I'm giving the answer for them?
sir, but the same thing you have mentioned in different ways, no sir.
That's
EC
what.
minus EV.
Arre. First answer my question. What is your name? Rajavelu.
Yes, sir.
Are you there when the people are asking the doubt? Same doubt two people has been asked. Huh?
Yes, sir.
What is the reply that I have given?
You said you will look into it and
No. I didn't said I looking at it. Please work it out. Okay, on your own you will get the answer. That's what I told. Huh? Spend some time at least. Okay. If not, I'll discuss. Huh?
Okay.
Yeah. It's going to be very simple. Just you sit and write the band diagram and try to analyze it. Fine.
Okay.
Rohit.
Good afternoon, sir.
Very good afternoon.
Sir, I doubt in yesterday's lecture.
Fine, go ahead.
Sir, you said recombination and scattering both are collisions.
Yeah.
But the scattering is the action taken place at distance, na. So how scattering will be a collision?
Collision means it has to happen physically always. Have you studied your +1 +2 physics? There are collisions you have in the physics you have studied the collisions, no?
Yeah.
Is it necessary that physically they have to meet? Collision means. Are you getting my question?
Yeah.
Is it necessary that to happen the collision physically they have to meet?
No, sir.
Yeah, that's what I have given, no?
Okay, sir.
Even it is action at a distance, but there is an interaction, no? Why it is happening? I have given very clearly that either it can be a force of attraction or it can be force of repulsion. Suppose if like charges are there, there will be force of repulsion, and unlike charges, there will be force of attraction. Because of that, what will happen? If interaction is taking place, definitely for every collision there will be exchange of energy and momentum. Okay, so that can take place even physically they are not meeting. Even at a distance, it can happen.
Okay, sir.
Got it?
And sir, I have one more doubt. You said two effective masses, conductive and density of states. So, in example, the examiner will give which mass we have to use.
Yeah, definitely. But if they have not given, also you must able to understand with context you are using. Suppose if I am writing with respect to conductivity in the sigma value, if you are writing there, obviously it is going to be conductivity. But if you see the equations that we have given for the Fermi energy level, you can very clearly see NC, NV are involved, no?
Yes.
What is NC, NV? Density of states.
States.
Yeah, that you must understand. Anyhow, they will mention the value, but you have to understand. If they have not mentioned also, you must able to understand in a position to understand what exactly it is.
Okay, sir. Thank you.
Yeah. Mahidar,
Good afternoon, sir.
very good afternoon, please.
Sir, as we have seen that EC minus EV is equal to EG, no, sir? The gap is EG.
Hmm.
And because of that, the average value means EC plus EV by 2 is equal to EG by 2. We are getting that one.
Hmm.
But in a mathematical way, EC plus EV equal to EG doesn't give any physical significance, no, sir?
Come again.
But mathematically, EC plus EV is equal to EG. Doesn't give any physical significance.
Okay. Oh, okay. I think I have written EG by 2 there.
Yes, sir.
Okay, that's why many people are asking. Okay, tomorrow I'll clarify that doubt. Don't worry. Okay.
Okay, sir.
Tomorrow I'll clarify. I think this is the 5th person you are asking the same doubt. Maybe I have written 1 second. Wait, can you tell me the page number?
Sir.
Okay, so no issue. I'll look into it. No problem. We'll discuss tomorrow.
Okay.
Yeah, Vinisha.
Sir,
Yeah.
sir, is hear me?
Yeah.
Sir, that fourth assumption once again explain me, sir.
Which assumption? Where? Can you tell me the page number?
Sir, I didn't get sir page number.
Which
I
assumption? Which assumption?
Sir, in
Okay, we are
location of
discussing.
EF by
Okay.
simple.
Got it.
At that time, my connection is gone, sir. That's
Okay, no problem. Have you listened to the third one?
yes, sir.
Similarly, you assume that the Fermi level is near to the valence band,
Yes, sir.
and draw the f of e comma t 1 minus f of e comma t, and identify the areas here. What is the concentration of electrons and holes? We'll get p greater than n. But in intrinsic, it is wrong. It is n equal to p, no, in intrinsic.
Yes, sir.
Yeah, you try to draw and you can get it. Similar type of graph. But
Similar
here,
to the third one, sir. Here, n is greater than p. Here, p is
p
greater
is greater than n. Oh yeah.
Yes,
Yeah.
sir. Thank you, sir.
Okay. Sohit.
Hello, sir. Good afternoon, sir.
Yeah, please.
So this doubt has been asked before, but I was not clarified.
Okay, which one?
The Fermi Dirac probability function states that at a particular temperature, at the given energy level, how many what is the probability of finding an electron, right?
Obviously.
Sir, but the physical significance of Fermi energy level states that at this energy level, EF, the probability of finding an electron is 0.5.
Yeah,
But-
that is what I'm going to. If you see the second statement that we have given, it signifies once T greater than 0 Kelvin. Please listen carefully.
Okay, sir.
T greater than 0 Kelvin. What is the statement that we have given? Exactly half of the energy levels, available energy levels, are occupied. I'm not talking about exactly at the Fermi level. Please try to understand this point. You may think mathematically when you are substituting, I'm taking since E equal to EF. Okay.
Okay.
You may get probability equal to 0.5. Fine, it's okay. But physically, what it is going to represent, you must understand. What it states is exactly half of the available states are going to be occupied. Where available states are present, both in the valence band as well as the conduction band, no?
Yes, sir.
Am I correct?
Yes, sir.
Now, again, same numerical example. There are 5 into 10 power 10, valence available states are present, and same number you take it for it's not the practical case. Okay, I'm giving the example. 5
Okay.
into 10 power 10, even in the conduction band also.
Okay, sir.
Now, out of this, okay,
Yes, sir.
suppose you take 2.5 into 10 power 10 are occupied. Okay.
Okay.
Nothing but not 5 into 10 power 10 you take, all the energy levels present in the valence band are filled, and all the energy levels which are present in the conduction band are empty.
Okay.
Now you increase the temperature, what will happen?
Some electrons goes to the conduction band.
From valence band, they will go to the conduction band. Now tell me how many number of states are occupied?
Same number.
Yeah, that is what it indicates.
Okay, sir. I understood that, but the definition of the function, what does the definition of the function states? It represents probability that a particular energy level is occupied by an electron.
Obviously.
But it means in the sense that at E is equal to EF, that energy level, at that energy level, how many electrons are being occupied? That's what the function says. The definition of
not how many, whether it is occupied or not.
Yeah, I mean the probability of occupying. That's what the function says, right?
Sir, okay. I will come to your point only. If probability is 0.5, can you say it is present? The electron is going to be present?
Means at least there is a chance, right?
No,
sir?
Answer my question first. Is it? Can I say electron is present?
I mean, half of the chance is present. I mean,
the
ratio of 0.5.
See, one second. Yes or no? You tell me. I'll give the tough question. If I say probability is 0.5, can you say, okay, exactly electron is going to present there? Yes or no?
Probability itself says
what
is the chance?
No, please listen to my question. You tell me answer yes or no. I'll further explore. Okay, don't worry. I'll give the answer for you.
Okay, sir.
Answer yes or no.
We cannot say, sir.
No, we cannot say. Good. Yeah. Now, there is a chance that, okay, at a particular instant of time, okay, conditions are such that there can be an electron, but it is not going to be staying forever. Within no time, it can fall down to the valence band, or if energy is given, it can enter into the conduction band. Are you understanding? Because you are not saying either, you cannot say yes or no. It depends on so many conditions now.
Yes, sir.
Okay, so those conditions may decide it can present for a moment and it can enter into the valence band, or it can move into the conduction band, energy is given. In that way you can understand. But if you take whatever we are talking about, the conduction band and valence band, okay, there is a certainty. Okay. Are you understanding my point? Even there also, if you see the numerical problem that we have solved, f of e comma t we have calculated, no?
Yes, sir.
Now you see the value, how much it is, 0.0 something you are having. Am I correct?
Yes, sir.
And but still we have calculated how many number of electrons are going to be present in the conduction band. We got in the order of 10 power 15. It's not a small number, no?
Yes, sir.
Are you understanding my point?
Oh, okay, sir.
So even though probability is very less there, still I have 10 power 15 orders of magnitude of electrons in the conduction band. But what you must understand there is, suppose you take, if you remember the NC value we have given, no, it is order of 10 power 19 in case of silicon.
Yes, sir.
But what you got 10 power 15 means there is 4 orders of magnitude difference.
Yeah.
Are you understanding?
Yeah,
so
sir.
because many number of states are present, always there is a chance that electron can move from valence band and it can occupy the conduction band. But here what you must understand is, it is not going to stay forever there, because it is an unstable state. It has to come back. It's a recombination process. And that is the reason why many times I mentioned electron hole pair generation and recombination is going to be a continuous process.
Okay, sir. One more doubt, sir. Sir, if at all we think EV, I mean, the top of the valence band is, for example, the 1 electron volt. I mean, for example, the EV is equal to 1 electron volt.
Okay.
And then the energy cap is another electron volt. And the bottom of the conduction band will be 2 electron volt.
Obviously.
So whenever the electron present at EV, if you give 1 electron volt of energy, it goes to conduction band, right? What if we give 0.5? Will it go to 1.5 and come back?
Maybe, but you are not in a position to sense it also. Actually, it may excite, but not to the it cannot go into the conduction band.
Okay, it cannot go to the conduction, but will it go to forbidden gap and come back?
Forbidden band where it can stay, because there are no energy levels that are present, no?
Okay, it will not stay. Whether will it go till there and come back or not?
Yeah, that maybe. No, my sense of asking you is, whether it is going or not, it depends on how much energy you are giving. It may, okay, but it cannot find a position there.
Yeah, there obviously there are no positions, but
Yes.
will it go or will
No,
it stay there only in
no,
valence
it
band?
No, it can go. That's what I'm taking. When you are, these points we are going to discuss when you are discussing about optoelectronic devices. 3 different what you call transitions. One is if you give the energy less than the energy gap, exactly energy gap, more than energy gap. Less than energy gap, it can move to a certain level, but it cannot find any energy level. It come back.
Okay.
Got it?
Yes, sir.
But exactly you give edge it is going to be. If you give higher energy, it can move into the higher energy level in the conduction band.
Okay, sir.
Got it?
Yes, sir. Yes, sir.
Okay.
Thank you, sir.
Yeah.
Hello?
Hello. I think this is the 4th time you are asking, man.
Sir, last doubt, sir.
You need to give chance for others also, no?
Yes, sir, last doubt, sir.
Yeah, please go ahead.
Page number 75, sir.
Yeah.
Sir, here you wrote EG equal to EC plus EV.
I wrote?
Yes, EG is equals to EC plus EV, sir.
Where?
Here, silicon EG by 2.
It is 0.55 electron volts.
You neglected the 0.0128, sir, electron volt.
Which one I have neglected? This is example I have taken to compare what is the energy gap of silicon. It is 1.1 electron volt. Half of it is how much? 0.55
Yes, sir.
electron
Okay,
volts.
sir.
It's not related to 0.018.
Yes, sir.
Okay, fine.
Okay, sir.
Hello.
Yeah, please.
Yes, sir. Please go to second last problem.
Second last. This one?
Yes, sir. Only I want to take a photo of question.
Huh? What do you want?
No, sir. Sorry. And please
You
go
have
to second slide.
you have any doubt?
No, sir. No doubt. I want to take a photo.
Good afternoon.
Rohan? Yeah, please.
So yesterday we discussed about atomic separation line.
Ah.
So can we say that as we increase the temperature, the atomic separation line shifts towards right side, and so the value of Eg decreases?
May not be exactly, because your interatomic distance depends on many parameters. Okay, I cannot say only with one parameter it is going to shift. It is not certain. There are many other effects also you need to consider.
So, but this statement is true that if we increase the temperature, the Eg value decreases.
Yeah, it doesn't mean that it has to shift. There are other effects also. You can think in other way that your electrons, particles are going to get the energy and they can easily move. Okay, because for conclusions, when you are making, there are different possibilities and different make a conclusion. Okay, and when you are giving general statement, again you need to be very careful. You need to consider many parameters. Okay, not based on one parameter. Okay. Yeah.
Yes, sir.
What